Thank you everyone for coming. This is the second seminar presented by the UCLA Nano Lab. Today's talk is going to be on our DualBeam system. It will be a brief introduction to how it works, some of its basic operation, what it could do for your research, and of course, how you can use it yourself. My name is Noah Bodson, and I'm the primary engineer in charge of this system. So let's get started. So when we talk about a dual beam system, there are two beams associated with it. The first is the SEM, or the scanning electron microscope. This is a beam of electrons that is focused down to a point, and that point is scanned over your sample. And as you scan that point over your sample, you collect the various particles that are ejected from your sample, and you produce an image by collecting those particles. Here's an image of a tungsten foam that was produced by a user some time ago. And you see you can get pretty nice pictures through this technique. The second beam on the system is the ion beam. It operates in the same principle as the electron beam, except instead of shooting electrons at the sample, we're shooting heavy ions. And so because they have more momentum, when they interact with the sample, they eject more than just light electrons that are collected. They also eject the material of your sample. So you're able to do local damage to your sample. In this example, you see we have a cross section that was produced. So when the beam comes down and hits the sample, we get both electrons ejected as well as your material that was impacted by the heavy ion beam being ejected. This is the basic layout of the system. The samples are loaded into a vacuum chamber, and there are two columns. Again, this is a dual beam system. There's the electron column, which is the vertical column coming down, and then we have the ion column off to the side. On the inset on the right, you can see the relative orientation of the two beams as they come down and hit your sample. When you're doing SEM imaging or electron beam imaging, you typically will have the sample not tilted so that the electron beam is coming perpendicular to your sample. And then when you want to use the ion beam, you want the beam coming in and hitting your sample perpendicular. And so we will tilt the stage. And this gives us an excellent view with the electron beam to look at the sidewall of the hole you produce with your ion beam. In other words, looking at the cross section of your sample. So the ion beam comes down and hits your sample and cuts away material. And then the electron beam can view the sidewall of that cut. So the basic principle of, I suppose, beam microscopy is you're focusing a beam of particles, whether it be electrons or ions, down to a point. And this point gets scanned back and forth over your sample. At each point, you have detectors collecting some of the particles that got ejected from your sample, and the number of particles that these detectors collect will determine a bright or a dark area of your image. Now, when the beam hits, again, this is referring both to the electron and ion beam. When the beam hits your sample, there's a bunch of scattering events that occur, and the volume in which those scattering events occur is called the interaction volume. And this interaction volume is important because that is the volume from which your ejected particles are coming from. So if you want to collect signal or produce an image of your sample that's very sensitive just to the surface of your sample, or if you have a thin membrane and you just want to image that membrane, you need to reduce that interaction volume so that it only covers the top surface of your sample. To do that, we can lower the energy of the beam. So the energy of the beam will determine how deep the scattering events will occur in your sample. Sometimes, though, you want to look really deep in your sample. Say you have some passivation layer on top of a circuit, and you want to look at the circuit elements below that passivation layer. In that case, you will want to increase this interaction volume so that we're sampling ejected particles from a deeper area and hopefully down to where your circuit is. So in that case, we'll increase the energy of the beam or increase the voltage of the beam. Another way to change the beam is to change its current. Naturally, that will change the number of secondary or backscattered electrons or particulates that are ejected from the sample. That will change the quantity and lead you to higher count rates for your detectors and give you a larger signal to noise ratio and get a clearer image. Unfortunately, though, when you do increase your current, you're increasing the spot size, so you're also decreasing the resolution. You see I have here on the picture labeled two things, backscattered and secondary electrons. So these secondary electrons are electrons that are knocked out of your sample due to the incoming beam, due to scattering events, where the backscattered electrons are electrons from the beam that are directly reflected back after scattering off of a nuclei in the sample. So the backscattered electrons will have a similar energy as the incoming electron beam, whereas the secondary electrons will have a very, very low energy. And those are typically what are collected when you produce your image. So one of the interesting things about this interaction volume is when you are scanning the beam over an edge or a cliff, as you see on the right inset, we're able to collect signal not only from particulates that are particles or ejected secondary electrons that come out of the surface of the sample, but they'll also be coming out of the side of the sample. So you're able to get a stronger signal when you're scanning the beam over an edge feature. So you see on this image, throughout the crystal structure, all the little steps have a bright tinge to them. And this is due to this edge effect of being able to collect more signal, more secondary electron signal at these little steps. So here's a picture of the inside of the chamber. Right down the center, we see the electron column or the pole piece from which the electron beam emerges. There's another large column coming down from the left side, which is the ion beam column. And you can see that they meet at some angle in the center. And then there's a couple cages we see, one behind the electron column, which looks like a cone, a conical cage. That is one of our detectors called the ETD, or Everhart-Thornley detector. And then we also have another cage in the front called the CDEM, or Channel Detection Electron Multiplier. So these are two detectors which collect, again, these secondary electrons that get ejected from your sample. The ETD, being off to the side, has a large amount of directionality to it, and we'll talk more about what that means. There's also a third detector not visible, which is called the TLD, or three lens detector. That is able to collect signal or particles that got ejected and go back up through the pole piece. And so there's no directionality to it. And we'll see some examples of that in a second. All these detectors, while they primarily operate in secondary electron mode or collecting these low energy secondary electrons, they do have a backscattered electron collection modes, but we don't have a dedicated backscatter detector, which is optimized for collecting those energies of electrons. But we do have those modes and they do work. But in general, we are going to be working in secondary electron mode on our system. So here's an example of the ETD, or the highly directional detector. And we see on the bottom, or actually throughout the image, that areas that are facing towards the right of the screen are brighter and areas on the left are darker. And this has to do, again, with the detector being relative to the chamber on the right side of this image, or relative to the sample on the right side of this image. So what this allows us to do is determine whether a feature we're looking at is a hill or a hole, or a bump or a hole. So because the right side of this large leg coming down the bottom of the screen, because the right side is brighter than the other side, we know that this is a hill, because if I know the detector is on the right side of the screen, I'm able to collect more signal from that face that is facing the detector, while the face on the left side of the feature is in the shadow or is being blocked by the hill. And so we're able to collect less signal. So it's a quick and easy way to determine what you're looking at, whether it's a hill or a bump. I'm sorry, I'm reading a part of the group chat. Please use my pointer. I suppose, are people able to see my pointer? And I will attempt that. Great, thank you very much. So here's the through lens detector. We saw this sample earlier, but this is a straight down view of it. And we see these edges are all bright. Now, if we were using the previous detector, these edges over here would be dark because this is a hole. So this surface would be in the shadow, would be blocked by this material here. And this would be a darker feature. So if you want to look down into holes where you don't get much signal coming out, it's more useful to use a through lens detector to get rid of that directionality so that everything comes out bright like so. And again, we still see all these edge effects that we were seeing here earlier. So this is just a summary again of what we've talked about. This is using the directional detector, or the ETD, the detector that has some directionality to it. And we see all the edges have a bright highlight to them due to the edge effect of the interaction volume. And then the edges that are facing the detector are even brighter than the edges that are not facing the detector. So that allows us to determine that this is a bump and not a trough or an etched trench. So the ion beam is going to work in a very similar manner as the electron beam in terms of scanning over your sample. But again, the ion beam is made up of heavy gallium ions, which have a nuclei, and it's not just electrons. And so there's a lot of more momentum from these particles when they hit the sample. And because of that, not only are we going to be ejecting secondary electrons and backscatter, well, there's not going to be backscattered electrons, but we'll be ejecting secondary electrons as well as your material that the beam hits. So what we did here is we told the beam to scan in this particular region, and we were able to etch away, I don't want to say etch away, mill away the passivation layer that was above this circuit, and it allowed us to see some of the features that were below the surface. This is just a brief summary of some of the specs of the system. It's a very large chamber, which is unusual for some SEMs. So we can handle up to 6-inch wafers. Anything below that, obviously, we can handle as well. Typically, we're looking at pieces and wafers. Pieces will oftentimes just be taped onto a stub or taped onto another wafer. And you can see some of the ranges of energies available for the electron beam and ion beam. And we're located in Engineering 5, if you're not familiar with that. I think I have a map coming up in a second. If you do ever get trained on this system, there is 24-hour access as long as you have access to the building. So there's a lot of flexibility for you to use this system. And then, of course, there is assistance by me or another engineer to operate the system for you. The image on the right is just an example of our, I think that's the 4-inch, maybe it might be the 6-inch wafer holder. If you're familiar with the layout of the campus, here's Engineering 4, here's the double elevators, and we are located in the back corner of Engineering 5 on the same floor, on the ground floor. So, what are some of the neat things that this system can do for you? We're going to go through each of these on the left side. This is an example of an AFM tip that was modified by a user. They had a particular material they deposited onto their AFM tip, and they wanted that material to be the probe on the AFM tip. And so here you see the surrounding material was cut out so that we just have this little bit of new material left as the probe. So number one, this system is an extremely good SEM. We consider it one of the best on the campus, but that's obviously for you to judge on your own. There are other systems on campus available to you, and I suggest you take advantage of all of them. But this one is available, and it produces some fabulous images the detectors, as we've talked about already, contribute to that, as well as the column. The second most common thing beyond just imaging that's done on this system is failure analysis, which typically encompasses producing a cross-section. So people want to use the FIB because it cuts the sample and allows you to see below the surface. So in the previous example, you saw a planar cut where we were just removing a square of material from the surface. Here, the primary purpose is to see a cross-section. So basically, a hole was cut so that we can now look with the electron beam down at an angle at this surface here so I can see what's going on down here, right? You produce some sort of device, and now you want to see, is what I produced actually there? In this example, which is what is typically done, we will deposit a strip of platinum down before we do the cutting. Actually, before even that, we put gold down everywhere. You see all this. This is gold that's been milled away a little bit, but because this top surface of the sample wasn't conducting, we put gold down. Then we put a strip of platinum, and then we cut a large hole, and then we do a final cleaning so that you get this clean cross section here. So we do cross sections of all different shapes and sizes. We can go up to about 200 microns wide, but typically we're doing things in the tens of microns, something 200 microns wide, depending on how quickly your material cuts, will take many, many hours. So for cost concerns, typically we're working in the tens of microns in all dimensions. Are those depositions done by the column or the sputtering before? So the blanket gold deposition over here is just done with a basic desktop sputter system. The platinum, which is deposited here, this is actually done with the focused ion beam system. So just like I can tell the ion beam to cut only in this area here to produce this hole, I can tell the ion beam to only scan in this area. And while that's occurring, I will stream a organometallic gas into the system that has some platinum attached to it, and it will decompose onto the surface just where I tell the beam to scan. So we have 3 types of depositions we can do in our system. We have tungsten, platinum, and carbon. Mostly we're using platinum just due to the speed of deposition, and it's conductive enough. So because you can tell the beam precisely where you want to go, you can do very quick prototyping. So features that you're seeing here, such as pillars and trenches and whatever, some marking, something like this would normally require doing various steps of lithography, depositions of metals, etchings, and this could take weeks, if not months, if you have to learn how to do this all on your own. So one of the great uses of the ion beam system or the dual beam system is to allow you to quickly prototype something you may want to make, at least on a small scale, or maybe not across a whole wafer, but at least across a small area, to see if it works, and then decide whether or not you want to go forward with developing the full-scale processing procedures. On the right side, this was a bitmap image, so we can load any image you want, and we can cut it away. It's not really used that often, but obviously if you need to take some pretty pictures for a paper, it may be useful as well. Another huge use for our system is in producing TEM samples. So TEM is a transmission electron microscope. It allows you to see atomic scale resolution on your samples, but there's a lot of requirements for your samples, one of which is the sample needs to be thin enough that the electrons from the TEM can pass through your sample. So to achieve that, what we can do is we can pluck out a chunk of your sample, attach it to a large grid. By large, I mean this is the size of a TEM grid, so this is typically, what, 5 millimeters across, roughly. And so we'll attach your sample to the grid, and then we'll thin it down to a level, a thickness that's compatible with TEM imaging. So typically we'll get down to about 100 nanometers. This is a reasonably complicated process. So in general, we don't have users do it themselves because it requires a heavy commitment on training. So we typically will do that for you. And there's a flat fee for this, and it includes everything. It includes the grid. All you have to do is, and includes a box. All you have to do is supply your sample. So this is heavily utilized by the community. And then, of course, we're not going to just make the sample for you. We can also do the imaging so that if you are not trained to use the TEMs here on campus, we can do the imaging for you as well. There is a 300 kV system on campus that we utilize that has that both TEM mode, scanning TEM mode, and it also has EDX available so you can identify the elemental composition of your samples at this minute scale. And again, all these services you can contact me directly for if you would like to use them. Occasionally, we have some people who want to do circuit edit on our system. So we've already talked briefly about depositing platinum to protect your sample during the production of a cross-section, but that platinum can also be used just as a conductor. So on our previous image, we saw that this hole was produced to expose the circuit below the passivation layer. And let's say you made a mistake in your design and you wanted to have a connection. We can go in and do something like so. We can also cut and break a connection. All of this is going to be dependent on what the local structure of your circuit is to make sure we're not going to damage other parts of your circuit during these processes. But we can do basic circuit edit. But again, this is going to work for small prototyping, in other words, for doing a few chips. But if you have like, thousands of chips that need to be modified due to an error, this is not going to be the technique for you. This is going to be for modifying or fixing a few chips. As we talked briefly about already, the system is excellent for just doing brief prototyping, just do proof of concepts before going in and developing full-scale processes in a clean room where you do lithography, etching, deposition, etc. So here a pillar was produced, and one of the newer capabilities of our system is the ability to do compression and indentation tests. So we have a Heisatron PI 85 Pico indenter, which is available, which can be loaded on our stage. And you can produce pillars in your sample using the ion beam. This would be done at a separate time. You would produce pillars that you can then come in and compress with this indenter. So this is a new capability we have, and highly unique, I believe. So you would take this needle, or this compression tip would be moved around and moved to each individual pillar, and you can get do compression tests. So quickly, some of the limitations of the system. Those of you familiar with electron microscopy know these things already. No magnetic materials. We are dealing with very strong electromagnetic fields when the beams come down and hit your sample, and magnetic materials cause a lot of disturbance to the imaging. If you do have thin layers of some of these materials, we can work with that. Second, we are operating in vacuum, so we don't want you guys touching your hands, touching your samples with your hands. Also in general, while we do load a lot of insulating materials, typically we will first coat them with gold or carbon to make sure that the incoming beam charge can be grounded away. Also, we're mostly dealing with flat samples. We're not doing much geological type samples that have a lot more surface topography. And while we have done some powders, in general, we try to stay away from powders just due to the risk they pose to the system. We do not have EDX on this system. However, there are other EDX systems on campus. Again, that's for doing elemental analysis and determining what your sample's made of. But if you do need that, we can direct you or help you with that service. Lastly, if you're familiar with other SEMs on campus, it's very quick to load and unload your samples for doing quick checks. This system has a much longer load and unload time. So we're typically doing longer sessions with this system, typically at least an hour. So if you just are looking for quick turnaround work, like I just need to inspect a wafer I just processed, other systems may be more compatible with your needs. So lastly, if you would like to use the system, I first always suggest that you get in touch with me first just to talk about what it is you need to do, and I can maybe guide you on whether or not the FIB is appropriate for your project or whether we can find other techniques that are maybe more appropriate. Initially, I will always operate the system for you just to make sure that we are getting the results that you want. If you find that you're going to be needing the system on a much more consistent basis, we will get you trained and so that you can do your own work. Depending on what you want to do on the system, if it's just SEM or you want to do FIB as well, or even TEM sample prep, there will be a number of training sessions that you will need to attend. The system is extremely accessible. There's an online reservation system. Again, there's 24-hour access to the system, as long as we can get you building access for after hours. Anyhow, the system is very open for you, and we want you to use it. And that's about it for right now. My contact information is there, and I highly encourage you to reach out to me. If you have any questions, please either type them in or you can unmute yourself. But I hope you have a better understanding of what this system is capable of. And thank you very much for attending.